Welcome to ClickMyProject.com. Now we discuss about the product for a combined SDC-SDF architecture for normal input-output pipelined Radix-2 FFT. Next we see the abstract for the product. Fast Fourier transform has played a significant role in digital signal processing field, especially in the advanced communication systems such as the orthogonal frequency division multiplexing and asymmetric digital subscribe line. All these systems requires the FFT computation must be high throughput and low latency. Therefore, the designing high performance FFT circuit is an efficient solution to the above mentioned problems. In particular, the pipelined FFT architecture is mainly adapted to addressing the difficulties due to their attractive properties such as the small chip area and high throughput and low power consumption. To the best to our knowledge, two types of pipelined FFT architecture can be found in the brief: delayed feedback and the delay commutator. Further, according to the number of input data stream paths, they can be classified into multipath or a single path architecture. The two classifications form four kinds of pipelined FFT architecture. Example for single path DC and multipath architecture are often adapted when the throughput requirement is beyond the theoretical limitation that the single path architecture can offer at the given clock frequency. However, they require concurrent read or write operation for the multipath input and output data. Therefore, the single path architecture could be appropriate in some cases when the system cannot ensure the concurrent problems. However, the arithmetic utilization is low compared with the 100% utilization of existing FFT architecture methodologies. We present an efficient combined single path delay commutator feedback and Radix-2 pipelined fast Fourier transform architecture, which includes a log2 n power minus 1 SDC stage, 1 SDF stage. The SDC stage processing the engine is proposed to achieve 100% hardware resource utilization by sharing the common arithmetic resources and the time multiplexed approach, including the both adder and multiplier. Thus, the required number of complex multiplier is reduced to log 4 of n percentage limitations. In this Radix FFT architecture, there is a common observation that one half data, some part or butterfly operation do not involve the complex multiplication at all, while the other difference part indeed they involve the complex multiplication. Hence, it has the appropriately to achieve the objective of reduce the arithmetic resources of the conventional complex multiplier by a factor of 2, leading to 100% utilizations. It's a deal to two consecutive complex input data to contain the complex number of which execute the complex multiplication. If so, we can minimize the reordering memory requirement while achieving the above objective to reduce the hardware resources for arithmetical resources for overall multiplying process. Next, we see the flow diagram for the product. We given the 16-bit data samples for overall FFT architecture. We given the 8-bit data input for our required apply our overall FFT architecture. This FFT architecture to consist the real and imaginary operations. The real and imaginary consider the 4-bit and another 4-bit to be considered the imaginary data bits. These real and imaginary data bits to be apply the pre-stage transformation process. The pre-stage transformation to represent the carry select ordering for addition process, carry look ahead order for subtraction process, both real and imaginary part also, and to calculate the weighted equation for overall FFT structure. The weighted equations mainly based on these equations e power minus j2 by n k by n. So these equations to be solved in mathematical manually and to calculate all the values, and we use the overall FFT architecture. Then we design the parallel multiplication architecture for our required weighted bit multiplication architecture, both real and complex process. We represent the 3-bit adder, subtract, 3 bit level of adder, subtractor and multiplier level. Adder means 4 bit and 4 bit subtractor and 4 bit multiplication. At the same wise the 8 bit and 16 bit also. Then we pass the adaptive split Radix-2 FFT transformation process for overall SDC-SDF based input output pipelined architecture. Then we apply these architecture and to present the stage by stage output process also, and to passing the postage process. This postage process to get the final transformation bits for both real and imaginary process. Then to design say all the process to be Xilinx software and to simulate the and synthesis the overall architecture performance level. This level to obtain the FFT structure, complexity and timing and power level also. Finally we see the output for the product. Our process for overall FFT architecture, then to run the Xilinx ISC project Navigator. Our process was developed in VHDL language, or then our process was doing the Xilinx 14.2 software. Then to open the ISC project Navigator, this Navigator to analyze the simulate and synthesis performance results for overall FFT architecture. Then to open the Xilinx ISC project and to select the main function, these functions to represent what are the input output present in overall FFT architecture. Then to select the simulation process for simulating performance analysis. Then to simulate the first FFT architecture and to run the final output process. This process was compiled successfully, and to open the Xilinx ISM project Navigator. This Navigator used to simulate our overall FFT architecture. We apply the given input data bits separate initially and to get the final data bits for overall FFT architecture process. This is the ISM project Navigator process. This process to apply the input for one by one for overall FFT architecture. These 8 bits to be split into the 4 bits and to passing the real and imaginary architecture process. This is our final simulation output data bits for required FFT architecture results. This is our given input data bits, and this is our final data output data bits. This is the simulation performance. Then go to the implementation work. This implementation work to represent the RTL and technological schematic and the diagrammatic representation for overall structure, RTL diagram and technological diagram. Then to open the synthesis report for device utilization summary and the timing summary for overall architecture. This is the required output architecture for our overall design summary, then the device utilization summary. This is the timing summary, this is the device utilization summary for overall architecture process. This summary to represent how many hardware resources to be presented in overall architecture. This is the timing results for overall functionality. These two are our required FFT results for final architecture.